Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to take a second and just imagine standing on a world that completely defies all of our earthbound intuition.
Oh, yeah. It really forces us to throw out almost everything we inherently expect from planetary physics.
Right. Like you're standing on a surface where a single year, so the time it takes for the entire planet to complete one full orbit, lasts only 11 hours.
Just 11 hours. It's wild to think about.
It is. And the ground beneath your boots is radiating at a blistering 1,340 degrees Fahrenheit.
Which, for those tracking in more scientific terms, we're talking about 725 degrees Celsius, or roughly 1,000 Kelvin.
Which is hot enough to melt aluminum.
Exactly. It's an absolute oven.
And then, you look up. And the star in the sky isn't this distant bright dot like we're used to seeing. It fills the sky. It looms just 3 of its own diameters away from you.
It's a mammoth orb of heat and radiation that just completely dominates the horizon. The sheer proximity to the host star alters the mechanical and geological reality of the planet so fundamentally that we are essentially looking at an entirely different class of celestial body.
And the craziest part is that this isn't some theoretical model or like a setting for a science fiction novel.
No, not at all.
This is a real rocky super-Earth. It's designated LHS 3844b, and it sits a mere 48.5 light years away from us.
Yeah, about 14.9 parsecs, which on a galactic scale is basically right next door.
Right. And the mission today, what we're really getting into, is something that I think fundamentally shifts how we understand our place in the universe.
It really does. Because we were looking at this recent groundbreaking research led by astronomers Sebastian Zeba and Laura Kreidberg. They're using the James Webb Space Telescope.
Specifically, it's mid-infrared instrument, right?
Yeah.
Now RI.
Exactly, MARI. And the thing is, we aren't just trying to confirm if this exoplanet exists anymore, or just measuring its mass.
We're doing exoplanetary geology.
Yeah, we are literally figuring out the exact mineral composition of rocks sitting on a world trillions of miles away.
Which is just, it's mind-blowing.
It really is the threshold we are crossing right now, this transition from kinematics to actual geology. Because, for decades, exoplanet science was primarily about detection.
Right, like measuring the radial velocity wobble of a star.
Yeah, or the minute dimming of a transit to just prove a planet was there at all. And then we moved on to characterizing atmospheres, looking at the light filtering through the gas giants.
But LHS 3844b, it doesn't have an atmosphere.
None. It is a naked, airless rock. So trying to determine the mineralogy of a solid surface across interstellar space, it pushes our observational limits to the absolute edge.
Because we have to map the astrophysics of orbital mechanics and thermal emission directly onto basically terrestrial geology, like magmatic crystallization and space weathering.
Exactly. And to even begin mapping those disciplines together, we really need to understand the absolute extremity of this planet's environment.
Because those physical parameters dictate literally everything about the rock on its surface.
Right. So it's a super-Earth. It's roughly 1.3 times the radius of our planet. And it orbits an M dwarf, which is a red dwarf star.
And these stars, they're smaller and cooler than our G-type zone, right?
They are. But because the planet is orbiting just 3 stellar diameters away, it's subjected to these phenomenal gravitational and radiative forces.
And the most defining consequence of being that close is tidal locking.
Yeah, tidal locking is the inevitable mechanical outcome for a body orbiting that closely, because gravity follows an inverse square law, right?
Meaning the gravitational pull from the M dwarf is much stronger on the near side of the planet than it is on the far side.
Exactly. And this differential pull creates a tidal bulge. The solid rock of the planet actually flexes.
Wow.
So early in the planet's history, as it rotated, this bulge would have swept across the planet's surface, generating massive internal friction.
And this friction, that's tidal dissipation.
Yes, tidal dissipation. It literally converted the planet's rotational kinetic energy into heat.
So it acted as a massive braking mechanism.
That's a great way to put it.
The star was essentially sapping the planet's rotational momentum over millions of years.
Right. And the braking continues until the system reaches its lowest energy state, which is a 1-to-1 spin-orbit resonance.
Meaning the planet's rotation on its axis slows down until it perfectly matches its orbital period.
Exactly. One rotation takes exactly as long as one revolution.
So the end result is that the same hemisphere is permanently locked, facing the star forever.
Yeah. We have a permanent day side and a permanent night side. It's very similar to the angular momentum exchange that locked our moon to the Earth, but just scaled up to stellar proportions.
That is, the day side is locked in an eternal high noon, just absorbing unmitigated radiation, while the night side faces the cold void of deep space.
And because we already know from previous phase curve observations that this planet lacks an atmosphere, the thermal physics are brutally simple.
Because without an atmosphere, you lose the mechanism of advection.
Exactly. On Earth, or Venus, or Titan, the atmosphere acts as a conveyor belt. It absorbs heat from the day side and physically transports it via winds and atmospheric circulation to the night side.
Right, it redistributes the thermal energy.
But on LHS 3844b, there are no fluids to carry the heat. The stellar energy hits the rock, it's absorbed, and it is re-radiated as raw black body thermal emission.
So the day side sits at that blistering 1,000 Kelvin.
While the night side temperature basically plummets toward absolute zero.
And the temperature gradient across the terminator line, so that twilight zone dividing day and night, it must be incredibly sharp.
Oh, incredibly sharp. It is a completely static, violently irradiated environment.
Which I guess brings us to the fundamental observational challenge here, because we don't have a direct optical image of this planet.
No, we don't.
The glare of the host M dwarf just washes it out, completely invisible light.
Yeah, it's completely lost in the glare.
So if we have this dark, silent rock sitting 48.5 light years away, and we can't even see it, how on earth are we extracting its exact mineral composition?
Well, we're relying on emission spectroscopy. Specifically, we're looking at secondary eclipses.
Okay, secondary eclipses. How does that work in this context?
So the secondary eclipse is really the workhorse for this kind of thermal characterization. When the planet passes in front of the star, which is the transit, we measure its radius based on how much light it blocks.
Right, that's the classic way we find them.
Exactly. But as the planet continues its orbit and moves to the other side of the star, it eventually passes behind it. And just before it slips behind the star, it's showing us its fully illuminated 1,000 Kelvin day side.
Ah, I see. So at that specific moment, the telescope is collecting the combined infrared emission of both the M dwarf and the planet's day side.
Yes, and then the planet slips entirely behind the star.
And during that eclipse phase, the telescope is only collecting the emission of the star alone.
Precisely. And the mathematics from there are straightforward in principle, though excruciatingly difficult in practice. We just subtract the star's baseline emission from the combined emission that we measured just moments before.
And the remainder, what's left over, is the isolated thermal signature of the exoplanet's day side.
You got it.
But the difficulty you mentioned, that comes from the contrast ratio, right? Because the star is still overwhelmingly brighter than the planet, even in the infrared.
Oh, absolutely. We are talking about isolating a signal that represents a change in brightness on the order of parts per million.
Parts per million. That is, the precision required is just staggering.
It is. And to pull that off, we are utilizing JWST's mid-infrared instrument, MIRI, alongside some archival data from the Spitzer Space Telescope.
But MIRI isn't just taking the overall temperature of the planet.
No. It's dissecting that isolated thermal emission across a very specific wavelength range, from 5 to 12 micrometers.
Why that specific range? Why 5 to 12?
Well, that 5 to 12 micrometer range is the critical window for a couple of reasons. First, from a purely thermodynamic standpoint, Wind's displacement law tells us that a black body object at 1,000 Kelvin will have its peak thermal emission right in this mid-infrared band.
So we are literally looking where the planet is shining the brightest.
Exactly. But more importantly, this specific spectral range contains the fundamental absorption features of silicate minerals.
Okay, wait. This is where we cross from astrophysics into geology, right?
Yes, this is the bridge.
We aren't just measuring how much heat is radiating. We are measuring how the specific molecular bonds in the surface rock are vibrating and emitting that heat.
That is exactly what we're doing, because different rocks have different spectral fingerprints.
So a rock isn't just a rock when it gets that hot.
No, not at all. The key phenomenon here is the Rest-Strahlen band. It's a region in the infrared where a material's index of refraction changes drastically, and that causes it to reflect or emit light in highly specific ways.
Okay.
So for silicate rocks, the silicon-oxygen bonds vibrate at frequencies that correspond exactly to the mid-infrared wavelengths that MIRI is sensitive to.
Oh, wow. So if you heat up a felsic rock, like granite,
right? Its silicon-oxygen bonds will produce a distinct emission spectrum with specific peaks and troughs. But if you heat up a mafic rock, like basalt, the lattice structure is different.
Because it has different stuff in it.
Exactly. The iron and magnesium content alters the vibrational modes. And so the resulting emission spectrum shifts entirely.
So the team, led by Ziba and Kreidberg, they basically isolated the heat signature of LHS 3844b, chopped it up into these wavelength bins across the 5 to 12 micrometer range, and effectively laid out the thermal fingerprint of the planet's surface.
That's it. And the next step was cross-referencing that fingerprint.
Like matching a suspect's prints in a database?
Very much like that.
Yeah.
They built extensive models using laboratory data from terrestrial rocks, lunar samples, and Martian meteorites.
And they computationally heated these samples to 1,000 Kelvin under high vacuum conditions, right? To predict what their emission spectra would look like if they were actually sitting on the surface of this exoplanet.
Yes, and that computational modeling requires immense rigor because optical constants, the properties that dictate how a material interacts with light, they are highly temperature dependent.
You can't just take the room temperature spectrum of a piece of basalt sitting in a lab and compare it to JWST data.
Exactly. The crystal lattice physically expands at 1,000 Kelvin, the vibrational frequency shift, and the emission bands broaden out.
Okay, so they had to extrapolate the high temperature spectral behavior of these mineral assemblages to ensure they were making a valid comparison.
Right, and when they ran those high temperature models and compared them to the actual JWST data.
This is the first major revelation.
Yeah, the resulting match, or rather the mismatch, was profound. They were able to confidently rule out a surface composition rich in felsic silicate materials.
Meaning there is no granite on LHS 3844b?
Zero granite. The crust is not like Earth's continental crust.
And why is that such a big deal? The absence of granite, I mean.
Well, the absence of a granitic or felsic crust is a huge piece of diagnostic data about the planet's entire evolutionary history. In our solar system, Earth is the only body with a massive inventory of granite.
Really? Just Earth?
Just us. And that's because granitic crust is not a primary geological feature. It doesn't just form right out of the gate.
Oh, okay. So how does it form?
When a terrestrial planet accretes from the protoplanetary disk, when it's first forming and undergoes its initial differentiation, the mantle that forms is ultramafic. It's very rich in iron and magnesium.
So the primary crust that cools from that early magma ocean is typically basaltic.
Exactly. It's heavy, dark rock.
So to get to granite, you have to actively refine that primary basaltic crust. You need some kind of massive planetary scale recycling engine.
And on Earth, that engine is plate tectonics.
Right.
The mechanism is fractional crystallization and partial melting. It's governed by what geologists call Bowen's reaction series. So when tectonic plates subduct, they drag oceanic crust down into the hot mantle.
But if you just melt basalt, don't you generally just get more basalt?
You do if you just melt it dry. The critical mechanism that produces the lighter, silica-rich continental crust is called flux melting, and that requires water.
Okay, so the subducting oceanic plates are pulling vast amounts of hydrated minerals, basically water trapped in the rock, down with them into the mantle wedge.
Exactly. And the intense pressure and temperature down there cause those minerals to dehydrate. They release water directly into the surrounding mantle rock.
And this water acts as a flux?
Yes, it drastically lowers the melting temperature of the peridotite in the mantle. This triggers partial melting, where the silica-rich components of the rock melt first.
Because they have a lower melting point.
Exactly. And this lighter felsic magma is more buoyant. So it rises to the surface, cools, and over billions of years, it accretes to form the granitic continental crust.
So water is basically acting as a chemical lubricant and a catalyst for this entire planetary refinement process.
It is the essential ingredient. Without the deep water cycle, the melting temperatures remain way too high, the fractional crystallization stalls out, and the mantle only ever produces heavy mafic melts.
So because the spectral data from this exoplanet shows an absolute absence of felsic silicates, we can deduce this massive chain of planetary history.
We can. It means plate tectonics either never initiated there, or if it did, it operated without the necessary water flux and just quickly seized up.
Wow. We are looking at a world stuck in a stagnant lid regime. It's completely bone dry.
Desiccated mantle, which, brings us to what actually is on the surface. Because when they ruled out the granite, the model showed that the emission spectrum from MRI was an excellent statistical match for primitive mafic materials.
So we're talking about rocks analogous to terrestrial basalt or lunar mare basalt, or maybe even just unrefined ultramafic mantle material heavy on magnesium, iron, and olivine.
Exactly. And basalt makes perfect sense for a geologically primitive world. It's the ubiquitous dark rock of the inner solar system. I mean, it forms the floors of Earth's oceans and the dark patches you see on the moon.
Right, but the research team didn't just stop at the chemical composition, did they? They wanted to determine the physical state of the rock.
Yeah, and this is where it gets really tricky. Because is the surface a solid, contiguous slab of cooling magma? Or is it heavily fragmented into gravel and fine regolith?
Like, is it bedrock or is it dust?
Precisely. And this is where they ran into a significant diagnostic challenge. When you model the thermal emission of a planetary surface, the macroscopic texture matters almost as much as the chemical composition.
Really? The texture changes the heat signature.
Oh, drastically. A solid slab of rock has a different thermal inertia and a totally different spectral contrast than a surface composed of highly porous, finely ground powder.
Okay, so what did their models say?
Well, in their initial models, extended solid areas of magmatic rock matched the JWST data beautifully. And crushed macroscopic material, like gravel, also fit the emission profile.
But didn't the models initially reject fine regolith, like the microscopic powder that we see covering our moon?
They did, and the physics of why it was rejected are fascinating. In a vacuum, a highly porous layer of fine dust acts as a thermal insulator.
Right, because there's empty space between the grains.
Exactly, so the thermal gradient in the top few millimeters is extreme, and that alters the emission spectrum. But critically, fine silicates generally appear brighter or have a higher albedo in these models.
But the JWST data indicated a very low albedo. LHS 3844b is a dark planet.
Yes, very dark. So logically, it seemed like the surface couldn't possibly be a fine powder.
But then there's a big but here, right? That assumption only holds up if you're modeling pristine, unweathered dust.
That is the exact catch. LHS 3844b is a naked rock orbiting 0.01 astronomical units away from an active red dwarf.
It's right in the blast zone.
It is subjected to an environment that actively and violently alters the physical and chemical state of the surface over time. This phenomenon is called space weathering.
And we've studied this locally, right? On the moon and on near-Earth asteroids.
We have studied it extensively.
So space weathering is driven by two continuous onslaughts: the solar wind, or in this case, the stellar wind, and micrometeorite bombardment.
Yeah. And because there is no atmospheric shield whatsoever, protons and heavy ions from the M-dwarf stellar wind are traveling at hundreds of kilometers per second, and they smash directly into the crystal lattices of the surface minerals.
That sounds destructive.
Oh, the atomic level destruction is severe. The stellar wind causes sputtering.
Sputtering? What exactly is that? Like knocking things loose?
Pretty much. The incoming high-energy ions physically knock atoms out of the mineral matrix. So in a mineral like olivine, which is an iron-magnesium silicate, the lighter oxygen and silicon atoms are preferentially sputtered away. They get knocked into space.
Leaving behind the heavier iron?
Exactly. And simultaneously, you have micrometeorites constantly impacting the surface at hypervelocity.
And these micrometeorite impacts aren't creating massive craters, right? They're tiny.
Right, they're microscopic. But they are melting microscopic volumes of the rock in fractions of a second.
Wow.
The localized temperature spikes to thousands of degrees, melting the dust, which then instantly quenches in the cold vacuum of space.
So it flash freezes.
Yes, forming these tiny droplets of melt glass that weld the surrounding soil grains together into what are called agglutinates.
Agglutinates. And within the rims of those microscopic glass agglutinates, the iron that was liberated by the solar wind sputtering, it precipitates out, right?
It does. It forms these nanometer-scale spheres of pure metallic iron. We call it nanophase iron.
And the creation of this nanophase iron that fundamentally alters the optical properties of the regolith.
Completely alters it. It drastically lowers the albedo.
Because the metallic iron acts as a strong absorber of visible and near-infrared light.
Exactly. The longer the surface is exposed to space weathering, the more nanophase iron accumulates, and the darker the soil becomes.
So it darkens the material and it suppresses the depth of those diagnostic absorption bands we were looking for in the spectrum.
Right. And so the team realized that if they applied the optical effects of severe space weathering to their regolith models,
the chemically darkened powder suddenly became a perfect match.
a perfect match for the low albedo, dark readings that JWST captured.
Wow. But wait, that introduces a huge problem, doesn't it? A massive degeneracy in the data.
It really does.
Because if solid, unweathered basalt matches the dark emission spectrum, and heavily space-weathered microscopic regolith also matches the dark emission spectrum.
And the spectroscopy alone cannot distinguish between the two. We are left with two radically different yet entirely viable geological models for the planet's surface.
So how do we choose?
Well, it forces us to look at the temporal dynamics of planetary geology. We have to look at time. Let's examine the first pathway, the fresh and active scenario.
Okay, scenario 1.
In this model, the surface is predominantly bare, solid magmatic rock. But we just established that space weathering is incredibly efficient at pulverizing and darkening solid rock into regolith.
Especially at a distance of 3 stellar diameters from an M-dwarf, where the stellar wind flux is just absurdly high compared to Earth.
Right, it's orders of magnitude higher.
Yeah.
So the regolith formation and maturation process would be exceedingly fast on geological timescales.
So if we are observing a surface that is still solid, bare rock today, it implies that the rock is very young.
Exactly. Something must be continuously destroying the regolith or paving over it with fresh material faster than the stellar wind and micrometeorites can grind it down.
And the only planetary scale mechanism capable of that continuous resurfacing is widespread active volcanism.
Yes. For the surface to be bare rock, LHS 3844b must be undergoing massive effusive eruptions, just constantly paving the dayside with fresh basaltic lava flows.
It would basically be a hyperactive magmatic world, a lava planet.
Pretty much. But then we have the alternative. Scenario 2, the old and weathered planet.
Right, so this pathway assumes that the planet is geologically dead, or at least highly inactive.
Yeah, and without continuous resurfacing, billions of years of space weathering have completely taken their toll.
So the solid primary crust has been relentlessly pulverized and chemically altered into a deep, dark, mature regolith layer.
A planetary surface, analogous to the lunar mare or the heavily cratered plains of Mercury.
So we have this ambiguity between an apocalyptic volcanic hellscape and an ancient, silent, dusty rock. That is a massive gap in our understanding.
It is, and to resolve this degeneracy from 48 light-years away, the astronomers had to look beyond the solid rock itself and search for the transient byproducts of the geology.
They needed a tiebreaker.
Exactly.
And in planetary geology, active volcanism always leaves a chemical signature, right? In the form of magmatic degassing.
Yes. When basaltic magma rises from the mantle and erupts onto the surface, it undergoes rapid decompression.
And the volatile elements that were dissolved in the melt at high pressure, they basically exsolve and escape into the vacuum as gas.
Like opening a shaken soda bottle. And the most prominent diagnostic volatile for mafic volcanism is sulfur dioxide, SO2.
Right, sulfur dioxide. Because sulfur partitions very strongly into the gas phase during the ascent of silicate melts.
It does. So even on an airless body, a steady state of widespread volcanic eruptions would generate a localized, transient exosphere of sulfur dioxide.
It wouldn't be a stable atmosphere, obviously, because there's no gravity or shielding to hold it long term.
Right, the solar wind would eventually strip it. But the continuous resupply from the erupting lava would maintain a detectable column density of SO2 gas hovering right above the active regions.
And MIRI is exquisitely sensitive to sulfur dioxide.
Oh, incredibly sensitive. The SO2 molecule has incredibly strong, distinct vibrational absorption bands at 7.3 and 8.6 micrometers.
Which is right in the sweet spot of the spectrum JWST was already analyzing.
Exactly. So if scenario 1 were true, and the planet was actively repaving itself with fresh lava to maintain that solid rock surface.
The SO2 absorption features should have been glaringly obvious in the data.
They should have been undeniable. So the team exhaustively analyzed the spectra, specifically searching for those 7.3 and 8.6 micrometer SO2 signatures.
And what did they find?
Absolutely nothing. Zero trace of it.
Wow.
The data placed an incredibly strict upper limit on the potential abundance of SO2, which effectively rules out any widespread, ongoing volcanic outgassing.
It is such a brilliant application of negative data.
Isn't it? The absence of the gas forces the collapse of the active volcanism hypothesis.
Because without the volcanism to constantly resurface the planet, scenario 1 just becomes geologically untenable. The solid rock would have been ground down by the intense stellar environment a long time ago.
Exactly. So the lack of SO2 pushes the evidence overwhelmingly towards scenario 2.
Meaning LHS 3844b is an ancient geologically stagnant world?
Yes. We are led by a rigorous process of elimination to the conclusion that it is a massive tidally locked analog to Mercury, covered in a deep layer of heavily space-weathered dark basaltic regolith, just baking silently under the relentless radiation of its red dwarf star.
Just building this deductive chain. Going from a tiny dip in the infrared light of a star 48 light-years away to ruling out granite through the physics of fractional crystallization to modeling the atomic sputtering of space weathering, and finally using the absence of sulfur dioxide to prove the planet is a dead, dusty rock. It's really a masterclass in modern astrophysics.
It's astounding what we can deduce now.
But, observational science is always about pushing the boundaries of certainty. While the lack of SO2 heavily favors the dusty regolith model, astronomers want a direct physical measurement of the surface texture, don't they?
Oh, definitely. And Ziba, Kreidberg, and their teams are already developing the methodology for the next phase of observation.
And this new methodology, it moves away from purely chemical spectroscopy, right?
Right. It focuses on the thermophysical properties of the surface, specifically how the macroscopic roughness of the terrain dictates the angular distribution of the thermal emission.
Okay, angular distribution. We're talking about thermal phase curves.
Yes, thermal phase curves. We mentioned earlier that as the planet orbits, it shows us different phases, kind of similar to the phases of our moon. So as it goes from transit to secondary eclipse, we are seeing varying fractions of the illuminated day side.
Right. But the way the total thermal energy increases as more of the day side comes into view isn't just a simple geometric function of the illuminated area.
Because it's heavily dependent on the texture of the surface.
Exactly. We are dealing with the physics of non-Lambertian emission.
Non-Lambertian emission. Okay, let's break that down.
Sure. So if a surface is a perfectly smooth, flat slab of solid rock, it emits heat in a relatively uniform, predictable pattern based on Lambert's cosine law.
It acts like a perfect radiator in all directions.
Yes. But a planetary surface covered in regolith is not smooth. It is highly porous, chaotic, and heavily cratered at both the microscopic and macroscopic levels.
It makes me think of the velvet versus leather analogy. That's a great way to visualize the optics here.
Oh, that's a perfect analogy. Like, a leather couch is smooth, right? It reflects and emits light pretty cleanly. But a velvet pillow is covered in millions of tiny, chaotic fibers standing on end.
Right. And when you look at the velvet from different angles, the fibers cast microscopic shadows on each other.
Which scatters the light and changes the apparent brightness depending on your viewing angle.
Exactly. Now apply that to the infrared. Those tiny velvet fibers are the grains of regolith and the walls of microscopic craters on the planet.
Okay, so when the star is shining directly down on the regolith, the heat penetrates the porous upper layer.
Yes. But when we observe that surface from an oblique angle, like when the planet is only at a quarter phase, we are looking across the tops of the regolith grains.
Oh, I see. We see the microscopic shadows cast by the grains themselves.
Yes. And these shadowed areas are significantly cooler because the porous vacuum gaps between the grains prevent efficient heat conduction.
So the shadows stay cold.
Right. And this creates what is known as the thermal beaming effect, or the opposition effect. A rough, dusty surface will show a very sharp, dramatic peak in thermal emission at a zero-phase angle.
Meaning exactly when the star is directly behind the telescope, illuminating the surface straight on and hiding all the shadows.
Exactly. If it were a flat slab of rock, that peak would be much broader and less dramatic.
So by requesting more observation time with JWST to precisely measure the shape of this thermal phase curve across the planet's orbit, they can mathematically extract the surface roughness parameter.
We are adapting a technique that has been utilized for decades in our own solar system. We use it to study the thermal inertia and surface roughness of asteroids and the moon.
But to apply the thermal beaming effect to an exoplanet across interstellar distances, that requires a level of photometric precision that only JWST can provide.
It does. But the implications of this extend far beyond LHS 3844b. Because if we validate this technique, we secure a universal metric for characterizing the geomorphology of rocky worlds throughout the galaxy.
We won't just deduce their mineralogy. We will have the capability to ascertain whether we are looking at exposed bedrock or vast oceans of sand or deeply pulverized impact breccia.
We are literally reading the geological textures of the cosmos.
Taking a step back to view the entirety of this analysis, the narrative arc is just staggering.
It really is.
We utilize the mid-infrared sensitivity of MIRA to peer into the 5 to 12 micrometer range. We leverage the Restrelin bands of silicate minerals to prove the absence of a water-lubricated tectonic engine, basically ruling out a granitic crust.
Right.
We identified the mafic basaltic nature of the primitive crust. We applied the atomic mechanics of solar wind sputtering to explain how space weathering darkens regolith, which created that degeneracy in the data.
And then we broke that degeneracy by confirming the absolute lack of magmatic outgassing.
Leaving us with the portrait of a massive, geologically dead, tidally locked Mercury.
It is an unprecedented synthesis of disciplines. I mean, we are taking the microscopic, laboratory-derived physics of crystal lattice expansion and nanophase iron precipitation and projecting it onto an astronomical scale.
It's incredible.
And as we continue to refine these techniques, the comparative geology of the galaxy becomes accessible. And that comparative geology brings us back to a pretty profound realization about our own origin.
Because every model we ran, every spectral template we applied to this data was anchored by our understanding of Earth and our immediate neighbors in the solar system.
Yeah. But the more we look outward, the more that baseline shifts.
We constantly search for Earth analogs, right? Driven by the assumption that the conditions fostering life are inextricably linked to the conditions of our home world.
But as we survey the rocky exoplanets, we must confront the statistical reality of Earth's geology.
What do you mean by the statistical reality?
Well, the very ground we stand on, this silica-rich, highly fractionated continental crust built by billions of years of water-driven plate tectonics. It appears to be a glaring anomaly.
An anomaly.
Yeah. We have surveyed LHS 3844b and found primitive basalt. We look at Mars, Venus, and Mercury and find basalt.
Earth is the sole proprietor of a granite crust in our solar system.
And thus far, we see no evidence of the tectonic engines required to produce it on the super-Earths we are beginning to characterize.
It really reframes the Drake equation in a deeply geological context.
It does.
We often hypothesize about the rarity of life based on atmospheric retention or the presence of liquid water or the stability of the host star.
But what if the greatest bottleneck to complex life isn't just the air above us? What if it's the immense, sustained, and specific internal geological machinery beneath us?
Is the water-fluxed fractional crystallization engine that continuously recycles carbon, builds continents, and stabilizes our climate over billions of years? Is that the true cosmic rarity?
That's a profound question.
I want you to think about that. The next time you find yourself holding a piece of granite, consider the billions of years of tectonic refinement required to forge it. It might just be the most unique material for trillions of miles in any direction.